All right, everybody. We had in class some new material regarding circuits, capacitor circuits, and now it's time to show a few examples of various circuits, not the simple ones that we showed in class, but something perhaps a little more involved. So let's start. Let's start with something like this. Capacitor. All right, we'll do another 3 capacitor circuit. This is a little different than the ones we looked at in class. Some similarities, some differences. So let's take a look at how we would do this. Let's put some numbers on here first. So let's say this battery is 28 volts. This is the positive side of the battery. This is the negative side of the battery. Let's call this C1, C2, C3, and let's say C1 is 7 microfarads, C2 is 3 microfarads, and C3 is 5 microfarads. And we want to analyze this circuit. And analyzing the circuit means the following. Let's see. Here's our guiding equation. Capacitance is charge divided by voltage. So analyzing the circuit means we want to find all the voltages and all the charges that exist at various points or places in the circuit. And when I say that this is the equation that we're going to be using, sometimes this is misunderstood. We're not going to just apply this equation once and find all the answers. We're going to have to apply this equation again and again and again. We'll apply it to capacitor C1, we'll apply it to capacitor C2, we'll apply it to capacitor C3, we'll apply it to any equivalent capacitors. This is the guiding equation, but we're going to use it over and over. Sometimes there's the thought that if it's the important equation, I'd do it once and it gives me all the answers. That's how powerful it is. But the power comes in applying it to multiple capacitors in the circuit. So anyway, let's start, and I can't stress this enough, that we need to draw these colors. All right, so here is my hot color. Then I alternate. I start with my hot color at the positive terminal of the battery, and I trace along the wire as far as I can go until I bump into something. Then I take my cold color and I do the same from the negative side of the battery. And now I'm just going to follow these wires as far as I can go until I bump into something. And then I have areas of the circuit that still have no color on them. So I'm going to go back to my hot color, and now I'm not going to change the color. I'm going to change the style of the line to a dash. Okay, and then I'm going to build my my ladder. Okay, my voltage ladder, okay, my voltage diagram. So let's see. Let me try and do this a little differently than I did last time. This is another kind of a ladder than the one I showed you in class. So anyway, let's do this. Here's one rung of the ladder can be the solid red. The other can be the solid blue. And we're going to make these long lines. Then I'm going to make a I don't have dashed blue, but I do have dashed red. Okay, so those are the three colors and styles that I have. Let me shift that a little bit. And now I want to put in whatever voltages I know. So we know this voltage from here to here. There's solid red to solid blue. And solid red to solid blue is what's on the battery here. And we know that on the battery, solid red and solid blue represents 28 volts. So I can put that into my voltage ladder here. This is 28 volts. Okay. And then we have a voltage here, which is solid red dashed red, and I can see that color combination right here on capacitor C1. It's the only component that has that color combination. And remember, it's two colors. Each component has two wires going to it, a wire coming in and a wire going out, and I have to look at both wires and look at the color and style of the lines for each wire, and it's the combination that I'm interested in. And so this is going to be C1. That's not a voltage, that's just the component that has that color across. Okay, and here this is the battery, has that color combination across, and then we have this combination here, dashed red, solid blue, and I have two components. I have C2 has that color combination across, and C3 has that color combination. Look at the two wires going in and out of C2, and I've got dashed red, solid blue. Look at the wires going in and out of C3. I've got dashed red, solid blue. So down here on my diagram, I've got C2 and C3. Both have that color combination. So immediately, because I have two components that have the same color combination, I know that those are in parallel. That was the definition of parallel. So these are in parallel. Okay, so that means I can combine those two. I can combine two capacitors in parallel and redraw the circuit. And if I do that, I'm going to get the following diagram. I'm going to get a battery with 28 volts across it. I've got C1, and then I've got, this is C1, and this is C2, 3 parallel. Okay, C2, 3 parallel. Right? It's a combination of capacitor 2 and 3, and they're combined using the rules or the equation for parallel. And if you recall, I'll call it this, CAB, cab, parallel equals CA plus CB. If I have two capacitors that are in parallel, call them A and B, then in general, now this is a general equation, right? This is a general equation. This is not specific to this problem. In general, if I have two capacitors, CA and CB, that are parallel, and I want to combine them and create one capacitor out of the two that's equivalent, this is the formula for making an equivalent capacitor. I add the two capacitances. So in this problem, I can say that this is going to equal C2 and 3, it'll be 3 and 5. This is going to be 8 microfarads. So C23P is 8 microfarads. And this circuit behaves exactly the same as my original circuit. That's why we call them equivalent. And the reason I'm doing this is because if I draw my colors, remember, I'm alternating back and forth. If I'm going to analyze this circuit and I want to apply my governing equation for capacitance, well, that means I have to apply it to capacitor C1 to figure out the charge on these plates, the charge on the plate here and the plate here. But to do that, I need to know V1. I need the voltage on that capacitor. Well, that means I need to know the voltage represented by this color combination. The solid red, dashed red. But if I look over in my ladder, I don't know that voltage. And so I can't solve the problem. I can't do the analysis. By the same token, I need to analyze this capacitor, my equivalent capacitor, C23P. And that means I have to be able to analyze the voltage across that capacitor. But that's a solid blue dashed red color, and I don't know that voltage. So I can't do the analysis. So I'm continuing to look back and forth at the schematic diagram and then looking over here at my color ladder to see if I know a voltage that I would need to apply my governing equation. And I'm not finding it, so I have to keep doing equivalent circuits. So again, this circuit I can't analyze, but I didn't waste my time because I look at this circuit now and I ask the question, is there anything in parallel? And I look and I see if there are any two components that have the same color combination across them. Well, I only have two capacitors. C1 has solid red, dashed red across, and C23P has dashed red, solid blue across. And those are not the same, so these two capacitors are not in parallel. So I ask myself, are they in series? If I walk through C1, must I then follow the wire and go to C23P? And the answer is yes. So C1 and C23P are in series. So I can combine them now in series. They weren't in series before, but they're in series now in the equivalent diagram. And so I didn't see, C1 is not in series with anything in this original diagram. I want to make this clear. C1, if I walk through C1, I've got a choice right here at this junction. I could go down to C2, or if I wanted to, I could also walk through C1, and at this junction, I could choose to keep going and end up going down to C3. So in the original diagram, C1 is not in series with anything. But in the equivalent diagram, C1 is in series because I no longer have any choices to make. I must follow from C1 directly down to C23P. So I'm going to make another equivalent diagram. I combine these two into one. C equivalent. Okay, this is 28 volts. And C, let's see this. Let's do C D E series. If I want to do the series combination of two capacitors, D and E, if capacitor D and capacitor E are in series, the series capacitance that's equivalent is going to be 1 over CD plus 1 over CE. That's a series combination of capacitors. That produces an equivalent capacitor. So that means that C equivalent here is 1 over 7 plus 1 over 8. Right? Because C1, we said way back here, is 7 microfarads. And C23P is 8 microfarads. So this, and I'm not going to show the microfarads, right? They both have microfarad units, so my answer here will be microfarads as well. Okay, so I'm just going to keep it simple. I can use this equation to figure out the equivalent capacitance. All right. Let's first draw our colors. And again, I'm going to make a pitch. I have no relationship with the company Wacom, but I am going to make a pitch for their tablets, a Wacom tablet. I don't know if you've heard of those, W-A-C-O-M. You have, look them up on Amazon. A Wacom tablet is a tablet that plugs into your USB port on your computer, comes with a pen, an electronic or digital pen, and you draw on the tablet next to your computer, and because of the software you can create the kinds of drawings that I'm drawing here. I have a touch or a pen enabled laptop, but even if you don't have one like that, with a Wacom tablet you can draw on the Wacom tablet and create images like this for yourself, and you can have, with the right software, you can do all these things yourself. And I love paperless, I love digital, so it's just a great tool. Otherwise, get some colored pencils, colored pens, highlighters, and make these diagrams. You can't do these problems without drawing the diagrams, folks. It's really not optional. If professional electrical engineers make diagrams in order to understand circuits, we need to do it too. Okay. Well, now look here. Well, first let's do the calculation. Let's figure out what this C equivalent would be. So I'm going to get my calculator, and I'm going to put in 7, and then I'm going to hit the inverse key, 1 over, and then I'm going to put in 8 and 1 over. I'm going to add those two, and then I got to do 1 over again, and I get 3.73. .73 microfarads. Okay, that's the capacitance. And the point is, this is an equivalent circuit, which means it behaves the same as our original circuit, all the way back up here. It's going to behave the same. If a battery is hooked to this circuit with 3 capacitors, and a battery is hooked to this 1 capacitor, and if the capacitances have the values that we've calculated, then the two circuits are identical. They behave the same. To the battery, it couldn't tell the difference between them. That's what we mean by equivalent. The advantage of this final equivalent circuit is I know the voltages. Look, I know the voltage across CEQ. It's 28 volts because I have solid red now. Right? I have solid red on one wire going into that capacitor and solid blue on the other wire going out of that capacitor. So I know the voltage is 28 volts, and I know the capacitance, so I can use my governing equation. So here's what I can do now. So I can say, here's a specific equation. C equivalent is Q equivalent over 28 volts. That's just my defining equation for a capacitor, C equals Q over V, but now it's a specific equation because I'm putting in a particular value here, CEQ. I'm going to solve for the unknown. The unknown is the charge, and the voltage I know is 28 volts. And how do I know that? Because I'm looking at my color map on this final diagram, solid red, solid blue, and up here I see solid red to solid blue is 28 volts. So I can plug that in. So the color map gives me the voltage, and I am sure that it applies to this capacitor because I've carefully drawn these things. So if I'm going to calculate this, I'm going to calculate, just remind you of this, our little equation triangle. Q equivalent 28 volts and C equivalent. I cover over what I don't know. So I don't know the Q equivalent. Right? So if I cover that over, what this says is these two are next to each other in my equation triangle, and next to each other means multiply. Okay? Over under means divide. Next to each other means multiply. So bottom line is Q equivalent is C equivalent times 28 volts. And if I put that in, I've got 3.73, and then I'm going to multiply. We've got 28 times, I'm going to get 104.5. 104.5 microcoulombs. It's charge, so it's coulombs, and this capacitance was microfarads. See this prefix here. So that micro ends up coming through in my answer, micro, but because I'm calculating charge, I get a charge, so it's microcoulombs of charge. 104.5 microcoulombs of charge. So that means on this plate is 104.5 microcoulombs of charge. And so I've got my first calculation of something that I needed. Remember, to solve the circuit means I have to find all the voltages and the charges. Well, I just found some charge. I found the charge on this equivalent capacitor. And as we discussed yesterday in class, this, on the previous schematic diagram, the previous equivalent circuit, the battery has to do the same thing, 104.5 microcoulombs. This battery here, this 28 volts, has to push the same amount of charge out onto a capacitor plate as this battery in this diagram because they're equivalent diagrams. The batteries don't know the difference. They would behave the same. So I'm going to still get 104.5 microcoulombs, but now it's not on C equivalent. Now I'm looking at this diagram. It's the charge on the plate for C1. Okay. And as we saw yesterday, that ripples through in series. Any capacitors in series will get the same charge on the plates. Remember, this capacitor and this capacitor are in series, so they get the same charge on the plates. 104.5 microcoulombs. Same charge on the plates. Now, I know the charge on capacitor C1, and I know C1, so I can calculate something new. I can calculate using my governing equation, C equals Q over V. That's my general equation. Let's write the equation that I would need to solve for, in particular, for the specific situation of capacitor 1. So now I've got some different things that I know. So let's do this. Let's say C1 equals 104.5 microcoulombs. That's Q over V1. And V1, so this is V1. That's the voltage across capacitor 1. This is V2, and it's V3. It's the same voltage on my voltage ladder, right? Because C2 and C3 have the same colors across them, they have the same voltage, so V2 and V3 are the same thing. All right, so now here's what I know and here's what I don't know. If I draw my diagram, I have 104.5 microcoulombs. I have V1 and I have C1. I cover over what I don't know. Okay, so what I don't know is V1. I don't know the voltage across the capacitor. I know C1 and I know the charge. So this equation triangle shows me that to calculate V1, I have to take these two numbers, which are over under, and divide. And I divide exactly in the way it shows. And I'm going to say V1 equals 104.5 microcoulombs divided by C1, and C1 was 7 microfarad. Let me check that. I think I remember that correctly. C1 is 7 microfarads. That's exactly right. That's what we had up here. Okay. So let's go back, crunch this number. This is 104.5 and 7. I get 14.9 volts. 14.9 volts. So V1 is 14.9 volts. So instead of calling it V1, I can replace this with its value, 14.9 volts. That's the voltage we just calculated. The voltage represented by the solid red, dashed red color combination that shows up across capacitor C1. And we now know that that voltage represents theirs, 14.9 volts. What this means is this. The solid red line here is the highest voltage in the circuit because it's coming out of the positive terminal of my battery. The solid blue line here is the lowest voltage in my circuit because it's coming out the negative side of my battery. This dotted voltage here is somewhere in between those two, which is what I've shown. I've shown this dotted line, dotted red line, is between the solid red and the solid blue. 14.9 volts means that this voltage here is 14.9 volts higher than the voltage here. Okay? And we know that this solid red voltage is 28 volts higher than this solid blue line down here. Well, I hope it doesn't take a lot of insight to see that I now can put in the voltage here between solid blue and dashed red. I can put this in as 13.1 volts. Look, when I go from solid red to solid blue, it's 28 volts. In this diagram here, I go directly from solid red to solid blue, one jump. Okay, that's going across the battery. Right? But I get from solid red to solid blue over here, I go one jump to here and then another jump to here. I make two jumps instead of one. The first jump is 14.9 volts big, and then I take another jump, but by the time I get to the solid blue, it has to be 28. Well, if the first jump was 14.9 volts, the second jump has got to be 13.1, so that by the time I make the two jumps, I get 28. It has to be consistent. This principle has a name. It's called the Kirchhoff voltage rule. So, voltages have to add up. Okay, it's that straightforward. Voltages must add up. Now that statement is a little bit broad and ambiguous. The only way that I can really make sense of that statement is to have this kind of a color map. Again, this is why we draw our colors. This color map makes sense out of all of this. This jump and this jump have to add up to 28 because they end up going between the same colors from solid red to solid blue. Right? We'll have other circuits where it can be a little more confusing when I have more components in it. I'll do an example of that next. But here's the principle being introduced. Kirchhoff's voltage law. Okay. So now I know all the voltages. Okay. I know from here to here is 14.9 volts. I know from here to here on my original diagram is 13.1 volts, and I know that from here to here is 13.1 volts also, because both of these jumps have the same color combination across them. Solid blue to dashed red, and solid blue to dashed red. And that color combination is 13.1 volts. Well, now I have enough information to apply my fundamental capacitance equation to these two capacitors, to C2 and to C3. Right? So I can apply this equation to both, and I know the voltage, right? So let's do it, and let's say C2 equals Q2 divided by 13.1 volts. This is the equation that applies to C2. And what I don't know is Q2. I don't know the charge. So Q2 is again C2 times 13.1 volts. multiplication, right? And C2 was, let's see if I recall, it's way back here. C2 is 3 microfarads. So this is 3 microfarads. So if I've got 3, so I got, let's see, 13.1 and 3 microfarads. I got 39.3 microcoulombs. Okay, that's the That's the charge on capacitor 2. 39.3 microcoulombs. By the same token, I can say C3 is Q3 over 13.1 volts, or Q3 is C3 times 13.1 volts. C3 was 5, I believe. Yes. Okay. So C3 is 5 microfarads. So I take that information, bring it back down here. So this is going to be 13.1 times 5, so 13.15 multiply, I get 65.5. 65.5 microcoulombs. And I'm going to adjust, because I'm using some rounded off numbers, I'm going to adjust here a little bit. I'm going to make this, let's see, 4.5. 4.5. So I'm going to make this. I'm going to make this 3. I'm just going to adjust these numbers because I know that I'm rounding off. I'm rounding off pretty heavily. I've rounded off these numbers here. And so I'm not going to get exactly the right number, so I'm going to make some adjustments here. You won't have any problem if you don't round off, okay? But when I'm working on the board here, I can't write 7 digits, so I'll make the adjustments here myself so I get the answers that I know I have to get. So anyway, on Q2 is 39.2 microcoulombs. So this is Q2. And this is 39.2 microcoulombs. And we already know that this is 104.5 microcoulombs. And Q3, 65.3 microcoulombs. 65.3 microcoulombs. Okay, and this is a 2. All right. Now, here's another example of a Kirchhoff rule where things have to add up. Look at these two charges. And remember we said we've been working with equivalent circuits. Well, we combined C2 and C3 in parallel, and we created this equivalent circuit. And in this diagram, we have that the charge on the capacitor plate is 104.5 microcoulombs. That doesn't look the same as up here. I don't have 104.5 microcoulombs here. I don't have 104.5 microcoulombs here. But add these two together. Add these two numbers together. and you're going to get 104.5 microcoulombs. It's not each individual capacitor plate gets 104.5, but the two in combination get 104.5. The charges, when we have parallel capacitors, the charges on the plates have to add up to the total, okay, that you get when you make an equivalent parallel capacitor. So that's a check. That's how you can check yourself. If these two charges add up and give you the same result as you got when you created a parallel combination out of those two capacitors, then you've done it right. Okay? In essence, down here, we've made the two capacitors into one. And so this one capacitor has a total of 104.5 microcoulombs of charge. Here I've just broken it into two capacitors, and the two together have to come up to 104.5, and they do. Okay. So we've solved the circuit. We now know all the voltages and we know all the capacitances. I know the capacitance on this capacitor. I know the voltage on that capacitor. I know the charge on this capacitor. I know the voltage on that capacitor. I know the charge on this capacitor. I know the voltage on that capacitor. We have all the information about this circuit. Okay? That's what I mean by analyzing the circuit, to find all the voltages and charges on the components. And that's what we've done. And we've done it by using our colors, our color map, and also this fundamental equation, the definition of capacitance. Okay. All right, so let's do another one. Let's see, we'll do this. So we have C1, C2, C3, C4, and C5. C1 is 2 nanofarads. C2 is 4 nanofarads. C3 is 7 nanofarads. C4 is 10 nanofarads. And C5 is 12 nanofarads. Okay, so there's the values, and let's put a 50-volt battery here, and let's solve everything about this. Okay, I'm just going to go through. The principles are the same that we just discussed. We're just going to go through. You can stop and pause the video at any point, slow it down. Make sure you can do this without just watching me do it, okay? I'm really going to encourage you now to stop the video and solve this yourself before watching me do anything. Just take this as the given information, just like in the book. If you found an example problem like this in the book, the idea is to get the given information and then close the book and solve it using the principles that I've shown you. And then you can turn the video back on and see if you get the same result that I got. Don't just sit and watch me do this. That's not going to help you very much. You've got to do it on your own first. Get stuck. Try and figure out why you're stuck. And then go ahead and try again. And then when you get some answers, compare with what I get. And if our answers are different, then look and see why perhaps you got off track someplace. But you can't learn physics by watching. Most people can't. By just watching the lecture. You have to do what the lecture is trying to show you to do. Okay, anyway, enough said. So we start with our diagram. Okay, so here's my map. All right, let's see here. Make a little more room here. Okay, so there are all the components. I've got C1, which has the same color combination as the battery. I have C2, which is solid red, dashed red. I have C3, which is dashed red, solid blue. I have C4, which is dashed red, dashed blue. I have C5, which is dashed blue, solid blue. None of them have the same, except these two, right? These two have the same, okay? So I know the voltage across C1 is 50 volts, okay? So I can immediately calculate something about that. I can immediately say that C1 equals Q1 over V1. So Q1 equals C1 times V1. And I know both of those. C1 is 2 nanofarads, V1 is 50. So it's going to be 100 nanocoulombs, 100 nanocoulombs. So I can say on here is 100 nanocoulombs on C1. Okay, I can immediately do that because I know a voltage. I don't know any of the other voltages, so I need to do some equivalent circuit work. And I see that there's nothing else in parallel. Is there anything in series? So let's take a look. If I go through C2, must I go through anything? No, because I have a junction here. I have a choice to make about which way to go. So C2 is not in series with anything. If I go through C3, must I go anywhere? No, I have a junction here. I have a choice to make about which way to go. So C3 is not in series with anything. If I go through C4, must I go anywhere? Yes, I must go through C5. So C4 and C5 are in series. This and this are in series. Okay, so I can do a series combination of those two. So I can redraw the circuit. $50. There's C1. There's C2. There's C3. And C4 and 5 are in series. So these are going to be C4, 5 series. This is C1, this is C2, this is C3, and C4 and 5 are in series, and they then are going to be 1 over C4 plus 1 over C5. And 4 and 5 are 10 and 12 nanofarads. So if I do that, I've got 10, 12, inverse, 5.45. 5.45 nanofarads. That's C4-5 series. Okay. Now I've got to do my colors. And I've got to make sure I do things the same way I did before. Okay, so let's see. Yep. That looks good. Okay, so there's my diagram. Okay, and now I look and I see on this equivalent diagram, I see that this dashed red solid blue combination across C3 is exactly the same that I have across this new capacitor that I just created. All right. So those two are in parallel. C3 and C45S, they're in parallel. So I can draw another equivalent. $50. C1, C2, and C3, 4, 5 equals C3 plus C4, 5S. And C3 was 7 nanofarads. So this is going to be 12.45 nanofarads. Okay, I do my colors again. Okay, this is C1, C2, and this is C3, 4, 5. Okay, and now I look and I ask if I go through C2, must I go through anything? Yes, I must go through C3, 4, 5. Those two are now in series with each other, so I can combine them. 50 volts. This is C equivalent. 1 over C2 plus 1 over C3, 4, 5. And that's going to be, let's see, C2 was 4 nanofarads. So I've got, let's see, 7 plus 12.45. C1 and C2 was 4. I get 3.03 nanofarads. Let's try that again. I got 12.45. I got 4. And I take over 3.03. Okay, 3.03 nanofarads. That's correct. I do my colors. And now I see, I know the voltage across. It's solid blue, solid red, and I know that because I know solid blue, solid red. It's the same as the battery. That's 50 volts. So this capacitor, this equivalent capacitor, that's 3 nanofarads big, has 50 volts across it. So I can figure out the charge on that. Okay, so let's carry on here with some calculations. We've done all our equivalent diagrams. So now we have some information. We can calculate another capacitor, this equivalent capacitor. So let's say C equivalent is Q equivalent over 50 volts. So Q equivalent is C equivalent times 50 volts. And C equivalent is 3.03. So we're just going to multiply that by 50, and we get 151.4 nanocoulombs. So on this plate is 151.4 nanocoulombs, and before we had calculated 100 nanocoulombs on C1. So we know this, 100 nanocoulombs, okay? But we're not done because we have all these equivalents. We've got to go back up through each equivalent and figure out what's going on in each one of them, okay? So this is still 100 nanocoulombs, okay? Because that's exactly the same in both diagrams, so there's 100 nanocoulombs there. But now I've got 151 nanocoulombs on the plate of another capacitor. Well, that's going to be here in the previous diagram. So this is going to be 151.4 nanocoulombs is on that plate. And because C2 is in parallel, or I'm sorry, in series with C345, our rule says it gets the same charge here, 151.4 nanocoulombs. All right. Well, now we can calculate some other voltages. So we can say, let's apply our standard equation to C2. So we can say C2 is 151.4 nanocoulombs over V2. And I don't know V2, but I know C2. So I can say V2 is 151.4 nanocoulombs divided by C2. And I do that math in C2. Let me just remind myself what C2 was. 4 nanofarads. Okay. So this is going to be 4 nanofarad. So 151.44 divide, I'm going to get 37.8 volts. 37.8 volts. That's V2. So let me go back and put that in my map, my voltage map, 37.8 volts for V2. So this is 37.8 volts. 37.8 volts. Okay? Well, looky. I know from solid red to solid blue is 50 volts. I now know that from solid red to dashed red is 37.8 volts. Well, if I jump, watch, if I take two jumps, one jump and then another jump down to blue, I've got to get 50. Well, if the first jump is 37.8 volts, then the second jump has got to be 12 volts, 12.2 volts. So that means that V3 is 12.2 volts. 12.2 volts. That's the voltage across capacitor C3. Okay. All right. Now, I still don't know V4 and V5, but we're getting there. I don't know this, and I don't know this. Okay. All right. So now, but I have the 50 volts here. Okay, and I don't want V50. I want 50 volts. So let's fix that. 50 volts. Clean this up here a little bit. 12.2 volts. Okay. And that's C3, right? All right, and so now we can come back down here. Let's see what we got. All right, so we now know the voltage here to here, okay? And now we can use the information that we have, the charge here and the capacitance here, and we can solve for the voltage here, which is across C345. Okay? So let's go and make that equation. So C345, let's see, how about if I make that blue? C345 is 151.4 nanocoulombs over, and what V is this? Let's see. We're looking here at the dashed red, solid blue. What did we call that way up here? Dashed red, solid blue. Oh, we already figured that out. Right? We already figured that out. That was 12.2 volts. We don't need to do that calculation. Well, let's do it. Let's do it. It ought to come out to be the same, right? And we called that V3. That was V3. So this is V3. We'll just do it. So V3 is 151.4 nanocoulombs divided by C345, and that's going to be 151.4, and C345 was 12.45. 12.45 is 12.2, right? 12.2 volts. So we already knew that, but this is just confirming to you that both methods get you there. Kirchhoff's voltage law will get you the same result as actually calculating out the capacitance equation. Okay? All right. All right, so now we have information from this equivalent diagram. And now we go back up to the next one. Okay? Now we can start to fill in some of these guys here and here, right? We've got C2 done. We've got to get now C3 and C4-5, because now we know the voltage. We know the voltage from dashed red to solid blue, okay? We know that voltage. We know from dashed red to solid blue. And now we have to figure out the charge on each of those capacitors. So let's do C3 first. C3, let's do C3 equals Q3 divided by V3. And so Q3 is C3 times 12.2 volts, because that was what we said V3 was. And C3, what was C3? Let's go back up to the top and see what C3 was. C3 was 7 nanofarads. All right, so 7 nanofarads. So we have 85.1 nanocoulombs. All right, that's the charge on capacitor C3. So let's put that at 85.1 nanocoulombs. So this is 85.1 nanocoulombs. This is still 100 nanocoulombs. This was the 151.4. And look, we're going to use Kirchhoff's charge relationship now. Look, I know that C345 was 151.4 nanocoulombs on the plate. Well, here's 85.1 of it. Okay? So this charge here must make up the rest of it. So I can take the 151.4 and I can $66.3. So this is 66.3 nanocoulombs. How do I know that? Because these two added together have to be the 151.4. Why? Because these two capacitors in parallel made up this one equivalent capacitor. So they have to have the same amount of charge, okay, total. All right, so anyway, there's 66.3. Now we come back to our original diagram. So let's go back up here. Let's put in all the ones that we know. We know 151.4 is here. 151.4 nanocoulombs. We know that this is 85.1 nanocoulombs. So here, 85.1 nanocoulombs. We know 66.3 nanocoulombs. Look here now. After C2, charge goes down onto C3, and charge continues to go and come down and go on to another capacitor. In my real circuit, charge goes down to C3, and there's still charge that goes this way. How much charge? 66.3 nanocoulombs. So this is 66.3 nanocoulombs. And since this is in series with it, this is also 66.3 nanocoulombs. Because C4 and 5 are in series with each other. These two are in series with each other. That's what created this capacitor here, the series combination of those two. So our rule said that in series, the same charge appears on the plates. Okay. All right, so now I know the charge on C5 and the charge on C4. I can calculate these voltages that I don't know yet. This voltage here and this voltage here. These color combinations on my voltage ladder. So let's see. Let's do C4. So C4, we'll go back to green here. C4 equals Q4 over V4. Right? And so the V4 is what I don't know. So V4 is going to equal Q4. So how much was that charge on C4? Let's go back up here and look. Okay, so on C4, I have 66.3 nanocoulombs. That's my Q4. So we'll put that in here, 66.3. 66.3 nanocoulombs. And C4 was 10 nanofarads. 10 nanofarads. And so this will be 6.63 volts. Okay, so V4 is 6.63 volts. So we go back up to our ladder, make that. So across here, V4 is 6.63 volts. This is 6.63 volts. Okay, and I'm going to round it off. 6.6 volts. All right. Keep my diagram a little cleaner. Now look. Look. Voltage adds up. I know from dashed red down to solid blue is 12.2 volts. Well, I'm going to do that in 2 jumps. I'm going to go from here, jump, jump. That jump, those 2 jumps have to add up to 12.2. Well, the first jump is 6.6. So that means the second one has got to be 5.6. 5.6 volts. So V5 has got to be 5.6 volts. Because together they have to add up to 12.2. Right, Kirchhoff's voltage law again. Okay. So now I've solved the circuit. I know all the voltages across every component, and I know all the charges on all the capacitors. That's the solution to this problem. Okay. Now I could ask you, how much energy is stored on capacitor C3? How about that? How much energy is stored on capacitor C3? So let's do that. Let's ask that question. Energy stored. We talked about this the other day in class on C3. Well, we said energy is 1/2 Q times V. Well, I know Q and V now. Is 1/2. What's the charge on C3? Well, let's go back up here. C3 is 85.1 nanocoulombs. 85.1 nanocoulombs. And the V3, that was the 12.2 volts. And so if I do this correctly, I'm going to get, let's see, 85.1 nano. I got to convert to nano. 85.1 nanocoulombs. 12.2. And then divide by 2. And so I'm going to get 519 nanojoules. Okay, 519 nanojoules. Right. That's the energy stored on the capacitor. Right. So this is the analysis of capacitor circuits. Hope this is helpful. Sorry for the scrolling up and scrolling down. It's the only way I can fit all the work on. Hope that doesn't make you crazy having to see me scroll up and down on here. Go back through and make sure you understand these steps. There's definitely going to be these kind of questions on the midterm. So practice, practice, practice. I would say start with the original problem that I gave you. Even if you've watched this solution now, go back, start with the original diagram before I started marking it up and the given capacitances, and just solve it on your own now. Even if you've watched this, and seeing all the steps, just go back and do it again. You're going to see things more clearly by going back and doing every step on your own without looking at this while you're doing it. Because that's what's going to happen on the test. You're going to have to do it on your own. Practice doing it on your own now before the test. Okay. Thanks, everybody.